So let's wait for some time to see if anyone joins. Then we can start. Yeah, I think we can start. So welcome everyone. This is NOC 26 NPTEL tutorial session on semiconductor devices for next gen FETs, more than more, a physics perspective. The course instructor is Professor Sudeb Dasgupta. I am Debashish from IIT Kanpur. So yeah, let's begin. So this is week 8. Okay. So the first question is, how does GIDL affect the subthreshold slope in a MOSFET, right? So you need to understand first what GIDL is. So GIDL stands for Gate Induced Drain Leakage. So one thing is sure, it is one of the leakage currents right? Primarily dominant in short channel devices. We'll see why. So yeah, so first, trends of trends of GIDL. So it can be generally seen in the transfer characteristics if you plot it in log scale, right? This is VGS, this is ID, log scale, right? So how does your okay, let me just draw. This is your this is how your normal IDVG looks like in log scale. So let's say around this is my threshold voltage, VTH, fine. So this is my on state or inversion. This is my sub threshold, right? So sub threshold or off state, right? And what we are we in the question it is asked that we should see how the subthreshold slope changes, right? So what is subthreshold slope? So the slope of this line. So subthreshold slope S is defined as partial derivative of log base 10 ID with respect to dVGS. Fine. What will be the unit? Unit will be volt inverse, right? Because log of some ampere is unitless, right? Similar, another quantity you must be, you must have heard about is sub threshold swing, that is SS. It is defined as 1 over S, and the unit is millivolt per decade. Decade is nothing but a unitless quantity denoting change of the argument of the log base 10 by one order. Okay. So ideally, we want larger S and smaller SS. Fine. Of course, because if my S or the subthreshold slope is larger, that means let me take a scenario. If let's say my on current is same and my subthreshold slope is larger like this, then I have less leakage current, right? Less leakage if S is higher. Fine. And this is so far. Wait a second. So this is so far. Wait a second. How can I change the view? Right. the video. Settings, just to background effects. So into the screen myself. Okay, that is not. Yeah. So am I audible and is it visible?
Yes, that's visible.
So far we are discussing gate induced drain leakage, right? So what I am motivating you to understand that what my subthreshold slope and subthreshold swings are, right? So subthreshold slope is defined as partial derivative with respect to the gate voltage of log of your ID, provided you are below this line, right? That means you are in this region or the subthreshold region. Remember the dominant current in this region. So what is the dominant current in this region? Dominant transport is diffusion, right? Dominant current in subthreshold is diffusion and dominant current in inversion is drift. Fine. And
Yes,
this
sir.
diffusion current is basically, as we have told you, that it is over the barrier current or thermionic emission. So that follows a voltage dependency of exponential nature, right? That is how in log scale you get a straight line. So that is why you are taking that slope, it is subthreshold slope. Okay. So we want, and subthreshold swing is just the inverse of that. Fine. So we want subthreshold slope to be higher and subthreshold swing to be lower, because if you see the pink line, if you see, let's say, if you see the pink line here, so this pink line, what is changing? Your on current I am assuming to be same, but then my off current or leakage current is very less. That is desired. Why that is desired? What will happen if, so what is the disadvantage of this? Let's say I have another condition like this. So what is the disadvantage of this curve? Higher off current or leakage current. That means you are turning off the switch. Let's say you are having a light bulb and you are turning off the switch. What do you expect? The switch to go shut off completely, but you are still seeing some dim amount of light, right? That is not desired. But what is the most crucial disadvantage of higher off current? Any comment?
Once again,
So what is the disadvantage if I go from black curve to red curve? That means your leakage currents are more, right? What is the disadvantage of having leakage currents more?
that means current will flow even when the MOSFET is supposed to be switched off.
Right? That translates to higher amount of drainage of battery, right? Lower lifetime of battery in your electronic devices.
Hmm.
This thing is called static power dissipation. Static power dissipation. okay, in CMOS parlance. Fine. So this is not desired, right? So GIDL is, so basically we are discussing gate induced drain leakage. So GIDL is one of such leakage currents, okay? It degrades. Okay, first let me show you the trend of or trace of GIDL, how GIDL shows up. Means from the terminal characteristics of MOSFETs, how will you know that there is a signature of GIDL? So this is log of ID, this is VGS. So ideally this is without GIDL, and let's say because it is a short channel device, so you will have something like this. I am exaggerating. This is due to Dibble, the threshold voltage shift that we have discussed. Fine. So this is your VDS equal to, let's say, 1.2 volt, and this is your VDS equal to 0.05 volt. So what are the significances? 1.2 volt is in your saturation, and 0.05 or 50 millivolt is in your linear region, right? So now what will happen if I have GIDL? So if I have GIDL, so you will see your characteristics go up like this. Okay. So this signature, this is for NMOS. So this is the signature of GIDL. So if your device where it is supposed to be off, it is not off, it is conducting significant amount of current, right? Which is not good. We need to find out ways to minimize this. Now we will see why this is happening. So what are the observations? That subthreshold slope, subthreshold slope S degrades, that means drops. As you can see that as your leakage current starts to increase, your subthreshold slope starts to reduce, and another option is it is dependent on VDS, right? This is 2 VDS. So as VDS increases, IGDL increases, right? And what are the other observation? It occurs very deep into the off state or in accumulation region, right? So let's say around this you will have your VFB, your flat band voltage, and around this you will have your threshold voltage. So this is VTH lin, this is VTH SAT. So why my VTH lean and VTH SAT are different? Due to which effect? Any comment? So due to which effect I get this threshold shift? We have discussed this in last session, right?
So lowering
This,
of temperature,
huh?
temperature variance.
No, there is no temperature variance, right? I am varying my VDS. So I am having a threshold voltage shift due to VDS. What is that effect?
So drain induced
Right.
barrier lowering.
It is double, right? Drain induced barrier lowering. We are getting this signature. And this is my GIDL, gate induced drain leakage. We will see why and how this is happening. But you need to first understand what are the characteristics that you from which you can conclude that you are having severe gate induced drain leakage in your device. Fine. So now another question would be what dictate this current level? That means this is we call it as leakage floor. Okay. So by the way, what I am plotting ID, right? So there is, I want to make sure that you understand this thing. So let's say if I have not covered it already, I'm just trying to repeat it. This is my IDS, right? There will be a diode. So this is my body. This is my drain. This is my source. So what are the currents? This is ID. This is IS. This is IB. Notation are like that. Fine. And what are these currents? These currents are let's say IBD and IBS. Do you understand this diagram?
Yes, sir.
So what is this and this? So IDS and ID are two different quantity. There will be other current sources connected to this, like the here your gate induced drain leakage will add another current source. So if you plot IDS versus VGS, you will not see any GIDL, right? To see the trace of GIDL, you need to plot ID and also understand that physically this entire thing is sealed, right? Physically you cannot access this entire thing comes in a package. So what you have access to is just these three terminals and of course gate, right? This entire blue stuff is in a package inside the device, that whatever is happening. So anyhow you will be able to just see the drain current. Is it clear that your ID and IDS are not same? So whatever we are plotting here is log of ID, not IDS. Fine?
Sir.
Right. So if that is the case, so we need to see how my IGDL generates, right? So these are the consequences that your subthreshold slope will degrade. It depends on VDS. It occurs in the accumulation. So below flat band region. Fine. So to answer your question, it worsens the subthreshold slope by increasing leakage current and reducing gate control. What do we mean by reducing gate control? That means the current is dependent on VDS, right? Which it is not supposed to be. The transistor primarily or the gate control of the transistor primarily states that current between two different terminals should be controlled by a third terminal. But as soon as your VDS starts to control your current, that means you are losing your gate control. Fine.
Yes, sir.
So this is what it is. Now I will show you how and where GIDL occurs. Okay. Okay. So let's take a device. Let's take this is your MOSFET. This is your body. This is your P silicon, P type silicon. This is your N plus. This is I'm blowing up the oxide means drawing a very larger oxide, which it should not be. It is just for representation sake. This is drain, this is source, this is gate. Fine. And what are the bias conditions I am interested in? I am interested in this region, right? Because I am discussing IGDL. So my VG will be less than VFB, VDS greater than 0. Fine. Let's say my B is grounded and source is also grounded. What I am interested in is this region. This region, what I am interested in. So what is the status of the device? So there I have holes because my device is in accumulation or in deep off state. Fine. So I'll just zoom this region up. So you have, let's say you have something like this. This is drain, this is oxide, this is gate. This is P type, and this is N plus type. And gate is N plus poly. Okay. Now my VGS or VG is less than VFB, VD is greater than 0, VB is grounded. Now I want to draw band diagram across these regions, across this and across this. So let's say this is 1, this is 2, and this is 1. So band diagram of case 1 is well known to you. So how will the band diagram of, so okay, just let me copy this. I am doing this because GIDL is the one effect, one short channel effect that most of the people misunderstand, right? Where and how this happens. So it is very important for you to understand. So let's say case 1 and case 2. So in case of case 1, what is the device structure I see? I see oxide, I see p-type semiconductor, I see N plus poly, and this terminal is my body, this terminal is my gate,
So you're
right?
talking about the left side of one, right?
Left side of 1 means 1, the cut line. 1 is the line across which I am drawing the band diagram. So
Okay.
basically, your line wall will be like this line, right?
Yes, sir.
You see, this is the line, right?
Yes, sir.
So in case of case 2, what do I see? I, s- I see oxide. This is N plus poly. And tell me what should be the other guy, other thing? This is N plus, right? And this terminal is drain.
Yes. Sir, but won't there also be a bulk, sir?
Yeah, yeah, there can be bulk. Let's say,
Maybe a bulk at the end, right? B type.
there can be bulk, right? This is
Okay.
B and this is your drain,
Mm.
right? Fine. But for the time being, you can ignore this. This is far away from the surface, right? What we are focused on is this region. What is happening in this region. So your this bulk is far away, right? This p-type region is far away. So that is why, for the ease of understanding, consider this. This is, let's say, your drain. So whatever you are saying will be very important when my this junction depth, this we call this depth we call it xj, junction depth. If this is very small, right? In those cases, for example, if xj is small, example in case of your FDSOI, more likely ultra thin body and box FDSOI. In those cases, as you have correctly pointed out, we need to consider that additional additional body contact. But there will be an insulator in between, right? If time permits, we'll discuss those things, otherwise not. For the timing, this is the simple case you have. So, what is your gate voltage? Gate voltage is negative. So, there are negative charges. So, in P-type semiconductor, what will be the uh, positive charges you have? You have only holes, right? Because your dopant ions are negative, Na minus. So, there will be holes in this region
Sir, why is there in N plus poly a negative charge, sir?
because your gate is negative.
Oh, okay, 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 okay.
Your this is negative, right? So, you will have negative charges all over it.
Okay, okay, yes, yes, yes.
Fine.
Okay. Sir, is this N plus poly like metal or something?
You can consider is like metal. Okay, this N plus poly is nothing but it is used to tune the flat band voltage.
Hmm.
Okay.
Okay.
So for the timing, you understand this as metal. Same thing will happen in case of metal as well because this is gate induced, right? So what are the if then again there is negative charges in this region. So what will be the positive charges in case of N plus? In case of N plus, what are the sources of positive charges? Come on, I think you can answer this thing. What are the positive charges in N plus?
Minority carrier roads.
But magnetic carriers won't be attracted easily, right?
Hmm.
Magnetic carriers will be thermally generated. So what are the easier option of positive charges? Nd plus, right? Donor ions,
Okay. So you mean the mobile ions?
immobile ions, right?
Okay.
Donor ions are there, Nd plus, and in case of P, there are Na minus. So what will happen? In this case, you will have a depletion region. This region, by the way, is also called overlap region, right? Fine. So now
Yes, sir.
let us draw the band diagram. Okay. So first, let's say your this is your EC, this is your EV, EV, right? Sorry, what am I doing? So this is your EC, this is your EV. The Fermi level is here, and the Fermi level for N plus is very near to this N plus poly, almost at EC. So when there is no transport, as is the case here, because there is insulator in between, so your this entire thing will move up, right? But again, you are applying what? You are applying negative voltage.
Yes, sir.
So that means effectively your bands will behave like this. So you have a negative potential applied. So EF in this region will be higher than EF in this region. Okay, this is your EV, and let's say somewhere here is your EC. So this is also your EC, and somewhere here you will have your EV. So your bands will be like this. Okay, this will bend very slightly because it is poly, and this bending is very at very higher place because your insulator Band gap is very higher. So what is the state of the surface from the band diagram? So here the gap, and note the gap here. Which one is lower, at the surface or at the bulk?
Sir, the surface.
That means at surface it is more p
P
type,
type.
right? That means it is holes are getting accumulated there. Fine. Right. Now let's draw this one. Both are almost at the same level before joining, okay? Before applying any voltage. So this is your EC and here it is your EF. In this case, EF is very nearby because it is N plus EV, right? Now, if this is here you are applying negative voltage, bands will move up. So in other sense, I can just draw this below like this. So it will be like this. So let's say this is your EI. So EI will also follow this and EV will also follow this. So what is the state now? This is the difference and this is the difference at the surface. So this is less N type, or the same thing we call it as depletion, right?
Yes, sir.
So this region there is depletion. Okay. Now understand one thing. And by the way, if you are concerned about this, so this is your applied potential, right? QVGB, and this is your applied potential QVGD, right? Now let's say you are increasing your drain voltage, fine. So increase drain voltage. What will happen to the bands? I will just draw bands at the right hand beyond the surface. EC, EV, EI. So what is happening at the bands? And somewhere here is your EF. So VD increase means this all bands are going down. Do you agree with that?
Yes, sir.
That means more band bending at the interface. And which location we are in? Now we are in this location, right? This interface we are talking about inside the overlap region. Fine. Now What are we seeing here? So this is what? This pink line is my valence band and the black line is conduction band. What we are seeing that at this location, valence band, EC and EV are looking at each other. Means they are at the same level, right? So what will happen? The carriers or the electrons here will tunnel through this region and reach to the EC of the right hand side, right? This is your depletion region. This is your depletion region. So inside the depletion region, from EV, electrons are tunneling through that depletion region towards the conduction band where it can carry current. In valence band, electrons cannot carry current, right? But in conduction band, electrons can carry current. And this leaves behind holes here and electrons here. Tell me if you have understood this much.
Sir, could you repeat the last point, sir, about increasing drain voltage?
If you increase the drain voltage, the right hand side bands will come down. This
Yes, sir.
will create a larger band bending. So if the larger band bending occurs, there will be a situation when your EV and EC at the interface will be very close to each other at the same energy level almost.
Sir,
And
EV or ECL or is it EF on EV?
EC and EV,
Sir, but EC is just placed highly above upwards, right, sir? So then
no,
how
that is
can
EC at
EV?
this place. I'm talking about EC of this region,
Okay, okay.
right?
Yes,
And
understood.
this length, this is your depletion width,
Hmm.
W depth. W depth is what? This is your W depth.
Yes, sir.
So what is happening? Your and also you remember that what is your electric field is in this direction
Okay.
because this is your D, this is VD, positive you are applying, VG, negative you are applying. So electric field is in this direction. So electrons will tunnel through from this valence band edge to this side of conduction band edge.
Okay.
Okay. So the same thing if I draw here. So inside this depletion region, I will get electron here and a hole here as well. This hole is basically at this location and these two are one energy band gap apart by this depletion region, depletion width. And now once this electron hole pair generates, this is my this is my excess electron and hole. This excess electron and hole will add up to excess current. This excess current will be part of the leakage current. It so happens that this particular leakage current, we call it gate induced drain leakage. So now where will these electrons go? This electron and let's say this is hole. So the electron is seeing positive potential here. So this electron will just leave through the gate. Electron will leave through the drain. So that will add up to additional ID. But what about the holes? These holes will move through the body, and this will increase your IB. Okay,
So,
clear?
sir, the current will push across the gate to the body.
Current to the additional current that we are having, we will see if we probe the drain terminal current ID and IB, body current, right?
Yes.
So this is what your gate induced drain leakage is. So remember that it is happening in the depletion region that is being formed inside the overlap region of your drain and gate. Fine.
Yes, sir.
So this is what is called gate induced drain leakage, right? So, and also note that what are you seeing? If VDS increases, GIDL increases, current level increases, and also if your VGS is becoming more negative, then also your IGDL increases. Why? Because if your VGS decreases, no, that is the equivalent thing of increasing VDS, because effectively it is depending on VDG, right? You're reducing VG or increasing VD has the same effect. Understood?
Yes, sir.
So this is what your gate induced drain leakage is. Fine. So let's move on then. Mathematically, it is not very complex, but I am trying to avoid that. It will have some exponential dependence on the field and also proportional dependence on the field, right? I would suggest if you are interested, you can read Professor Yanis Cividis book on MOS transistor modeling. Okay, use third edition. In chapter 5, you will have all these details, the short channel effects. May not be this much detailed, but you will get the idea, right? You will have something to start around. Then, what is the primary cause of channel length modulation in MOSFET? So, channel length modulation means, again, it is a
So,
one of
shortening of
shortening
GD
of channel length due to
drain voltage increase.
drain voltage increase. So, why does that happen?
So, because it becomes more reverse bias, which means the depletion width would actually increase. Again, the
So,
drain side.
basically, if you have greater than VTH threshold voltage, so you have something like this. You will have
You will have a channel
you
of
will
length.
have something like this, right? So
Mhm.
why the drain side depletion region is fatter than source side? And then you will have a channel like this. Let's say VD is equal to VDD. Let's say VD is more than VD sat, some saturation voltage. And this is greater than VTH. So you will have something like this. The channel will look, and there will be depletion charges. So your actual channel length was this, and this becomes your reduced channel length, and this is your LP, or the small length that is increased. LP increases as VDS increases, so that reduces. So L dash is equal to L minus LP, right? So if LP increases, your L dash decreases, that effectively increases your IDS. And what are the trends of channel length modulation? What are the characteristics? If you have VDS and ID, so you need to understand that in which plot we can see the effect of channel length modulation. So if this is without channel length modulation, so with channel length modulation, you will see
It will be above, right, sir?
something like this.
Yes, sir. Slightly linear.
And the consequence of channel length modulation is, in this case, what is your GDS? 0.
D 0, sir.
RDS? Infinity.
Infinity.
In this case,
RDS is not
GDS, comma RDS,
is finite, not zero.
finite,
Finite or not zero.
right? So
Mm.
even, so what happens, why it is called short channel effect?
Because channel effective channel length is reducing, right, sir?
No, short channel effect has nothing to do with effective channel length. Short channel effect is whenever your L is lower. Now let's say LP is, let's say LP is 1 micrometer, right?
Mm.
Not 1 micrometer, let's say 0.1 micrometer, and your L is 10 micrometer. Fine. So what is the ratio of LP and L?
So it will be actually less than 1.
100, right? 1 over 100,
Yes, sir, less than 1.
right? So this is called, we called a short, long channel device. Long channel device. So what do you think? How much will the percentage of change of channel length is around 1%, right?
Mm.
That we can ignore. But now assume your LP is 0.1 micrometer and your L is, let's say, 0.2 micrometer, or let's say 180 micrometer, 180 nanometer, 0.18 micrometer or 180 nanometer. Then what about that?
So this time it will be 5 by 9, right, sir? LP by L 5 by 9.
LP by L would be
5 by 9, 10 by 80.
10 by 18, right?
Yes,
Or
sir.
5 by 9. That is significant.
Okay.
We cannot ignore that, right? And this is your short channel device. Okay. So the portion of LP with respect to channel length, if it is very small, as in the case of long channel devices, channel length modulation we can simply ignore, right? But if it is for short channel devices, the portion of LP is significant, and that is why, because what was the historical reason? Let's say this is your long channel device, right? Long channel device channel length modulation will be something like this. the green curve on top of that black curve. People did not just notice, okay, people just did not notice that there is a change in current at all. But as soon as the channel length shortened due to law of scaling from generation to generation, people started to observe that this channel, this current is increasing with VDS, or my GDS is increasing, right? This increase in GDS, then they dug up, and then they found that it is due to this effect called channel length modulation. So as it was discovered in short channel devices, and also as it is more prominent and more important in case of affecting the behavior of short channel devices, channel length modulation is one of the short channel devices. Same with your GIDL, right? If your channel length is so large that your overlap length you can ignore, there is just no GIDL at all, right? But if your this portion of overlap regions are significant with respect to the channel length, then you will have significant signature of GIDL in your ID characteristics. That is why these all are short channel effects. Fine. So what are the consequences of short channel consequences of this? So your gain, intrinsic gain, your intrinsic gain of MOSFET is what? GM times RDS, right? Minus GM time RDS. You remember, right? Your RD comes into parallel with RDS. Now, if you do not connect any RD, that means it is open circuited, so only RDS is remaining. So, as your CLM increases, RDS decreases, intrinsic gain of the MOSFET decreases, which is bad for amplifiers, right? This we have discussed. Fine. So this is what your short channel effect is. Sorry, channel length modulation is. Okay. So next is velocity saturation. So have you heard of any other saturation before velocity saturation? So let's say, so this is in short channel MOSFETs, right? But what about in the case of long channel MOSFET? Long channel MOSFET. What is your IDVD characteristics look like? Is something like this, right? So there also I have some saturation. This is my VDS sat, which is almost equal to VGS minus VTH. So what is this saturation called? And why does this saturation happen in long channel MOSFETs? Before we go to velocity saturation, can you tell me? Try to attempt to answer that why does this current saturates?
So current will become independent, right?
independent of
Okay.
VDS. Why? Have you heard of this pinch of saturation?
Yes, sir. When VGS minus VG. When VD saturation becomes equal to VGS minus VG, equal to the overdrive.
That means at that moment, at the channel is triangular, and that
Hmm.
point is just at the drain, right? And at
Yes,
that
sir.
point, I have effectively no inversion charge,
Hmm. Yes, sir.
right?
Hmm.
Although there will be inversion charge, but that will be very little, right?
Hmm. Yes,
So
sir.
effectively, we assume that there is no inversion charge. So that means
Hmm.
what? Even if you increase VD, there is no change in the current.
Current will flow, but it will be constant.
Current will flow, it will be constant. Why does that happen? Your inversion charge is lowered and your electric field is becoming higher with increasing VDS. So
Hmm.
the product of those two will remain constant, right? We have
Hmm.
discussed this. So this particular phenomena is called pinch of saturation, which we generally observe in long channel MOSFETs as well, right? And this voltage is given by VGS minus VTH. This much you will know, right? This till this equation, I am assuming that you know.
Yes,
Now,
sir.
another kind of saturation occurs in case of short channel MOSFETs. That we call it as velocity saturation. We will discuss in detail what is it, but what is the consequence of it. Just let me motivate you that most of your circuits are designed for saturation considering this condition. This is your VD sat. That is what in the circuit designers always that it's a thumb rule, right? But what happens if you have velocity saturation? Maybe let me give you a scenario. Let's say if you have this is IDVDS, so velocity saturated short channel device. Okay, in that case, let's say in let's say this is how where your saturation pinch of saturation was supposed to occur, and you were supposed to design your device to be in saturation after this point, right, or linear below this point. But due to velocity saturation, it may happen that your saturation occurs at a much earlier voltage. This is your V V sat. Let's say this is called VD sat. This is due to velocity saturation. So what is the consequence? Consequence is that in velocity saturated devices, now the thumb rule of designing your circuit, whether it is in saturation or in linear region, is not same as it's supposed to be where the device is without velocity saturation, right? Now you in your device you have two types of saturation. So you have to be mindful about what your velocity saturation is. How do you see that your device is velocity saturation from the terminal characteristics, that mean output or transfer characteristics, right? So that is what we will discuss now. So first thing is what velocity we are talking about. So what is the, let's say your MOSFET, is in inversion. That we will assume. So what is the type of current we should have? Mostly your drain current will be, IDS will be, the transport mechanism in inversion is what? Drift or diffusion?
In inversion, it is drift, right, sir?
Drift, right? So what is the equation? Qn V times area, right? This Vd is your mu times E, right? There is only one type of carrier in inversion.
So
Does the
there's
equation make
also,
sense?
yes, sir, there's only one carrier actually in inversion.
Sorry,
There's only one carrier in inversion.
there is.
Only one carrier in inversion, right,
Yeah,
sir?
there is
That's
only
all.
one type of carrier in inversion, right?
Yes, sir.
Because MOSFET is a unipolar device in inversion. Only one type of carrier flows. It's not bipolar. Mind it. So this is that velocity what we are concerned about being saturated, right? So how do your velocity versus, so let's say this is your electric field,
The velocity saturates at high electric field, right, sir? Initially, it will increase
right?
and then it will just
So
saturate.
initially you will have a linear increase and then you will
Yes.
have some saturation. So your curve will be like this.
Mm.
Why does it happen? So in
It is
this
scattering.
case, it will be
Scattering.
mu 0 E. Mu 0
Mm-hmm.
is your low field mobility,
Mm-hmm. Yes.
and there is something called, let's say, VD
Scat-
max.
mhm.
So what is this VD max?
That's the maximum velocity which it will,
That is the
can be maximum velocity.
thermal velocity
Mm-hmm.
of the carriers. Okay,
Yes, sir.
it is generally given by 3 kT by m star, assuming MBDF or Maxwell-Boltzmann distribution function, right? Half mb square is equal to 3 by 2 kT. Just solve it and you will see. Fine. This is the maximum you can have. So why does it happen?
So due to scattering.
Due to scattering. What
Scattering.
kind of scattering?
So let's say Coulomb scattering.
Phonon scattering. What type of phonon
Yes.
scattering?
Lattice phonons.
No, actually, I am keeping you keep asking you advanced stuffs. Anyway, so this basically happens due to optical phonon scattering. Okay, at higher
So
energy.
optical phonon actually.
Hmm?
What is actually optical phonon? I thought
Okay.
phonons were just vibrations and
Yeah,
lattice.
phonons are vibrations of atoms or lattice atoms. So basically, phonons can be of two types: acoustic phonons and optical phonons, right? Acoustic
Yes.
phonons are those phonons which helps you carry heat, for example, or let's say carry sound from one place to another, right?
Okay.
You understand, right? That photon carry light from one place to another.
Mm.
Similarly, phonons or acoustic phonons carry sound from one place to another. It is the phonons in the medium that carries sound from one place to another, right? So in a vacuum, how it's a very good question for you to ponder about that how sound travels in vacuum, right? In a medium, you know that if you perturb anything or vibrate anything due to presence of temperature, you will see that your carriers are vibrating, acoustic phonons are getting generated, and that is carrying the sound from one place to another. Optical phonons are higher energy branches of phonons, right? So it has nothing to do with it emits light or what, anything like that, right? It is just that the energy of those phonons vibrations are very high.
Okay.
Okay, so those are called optical phonons. There are much
So,
advanced theories regarding this. Yeah,
sir, what will be the range of these energy of these optical phonons?
what are the
Order of energies.
order of
Approximate order.
energy?
Yes, sir.
So phonons, I do not think are measured in terms of order of energies. Okay,
Like
these are
joules or something.
no. I think it is. These are not measured in terms of joule. See, if you consider some energy, no, energy is distributed over. You cannot have, for example, you must have seen your. So how does your MDDF look like? MDDF looks something like this, right? And your FDDF looks something like this.
Yes, sir.
So what does this mean? This means that your particles or probability of finding particles over an energy is, or the particles are distributed over energy, right?
Yes, sir.
So you cannot say that I have this amount of energy for this particle. There may not be any particle or maybe some particles at this point. It all depends on. So you cannot just say that how much joules of energy I should have for optical phonons to have. That is not the correct measure of this. Okay, you have other quantities to measure that. For example, you have momentum, you have, what do you say? You have momentum, you have random velocities, right? But energy, you understand, right? Particles cannot have a single energy. It is distributed over the energy,
Mm. Yes, sir.
right? Just consider that this energy level is higher than whatever is in the acoustic branch of phonons.
Okay, okay.
Okay. So anyway,
So
that
when you say higher,
was
it means it is closer to that curve, right, sir? F of E is closer, FDD is closer to F of E, right, sir? Is
sorry,
that what you mean by, sir, when you meant that it has higher energy, is the optical phonons are higher energy than acoustic phonon? Do you mean to
right?
say that at FDDE, that is the Fermi Dirac distribution, is much more closer to that F of
Oh,
E curve?
by the way, phonons does not follow MBDF or FDDF. It follows something called BEDF, Bose-Einstein distribution function. Okay,
Okay,
just like photons.
okay,
Okay, so but these are some different concept. I don't want to go deep into that. Otherwise, this will cover the entire session. Okay. Whatever, if you have any particular query about phonons, you just email me. I'll provide give you some consolidated document, okay, for which will be easier for you to understand at the undergrad level.
okay, sir.
Does that sound good?
Yes, sir.
Okay, so the point is that yes, as at higher electric fields, of course your particle will have higher energy. E of electric field is your energy, and that will lead to opening up the optical phonons, and more optical phonon, one phonon is one scatterer, right? So more scattering, so your velocity gets saturated and your mobility drops severely. Fine, this is why your velocity saturation occurs. Now how do you model your velocity saturation? Because some questions, the next two three question, we have to have some mathematical sense of the velocity saturation. So that is why we'll just derive very briefly how my velocity saturation model will behave. Okay. So how can I model this curve, blue curve? So let's say I'm giving you more inputs. Let's say this electric field is called critical electric field or EC, and this line equation we can write at mu 0 EC. Is that correct? Mu 0 EC I can write, right? Because this is the slope of this line is mu 0, and mu 0 EC is this point, exactly this point on this line, right? So how can we model this blue line? So I have VD equal to mu 0 electric field for E less than EC, and VD equal to mu 0 EC or VD max for E greater than EC. So how can I model this? You have already modeled this, right? The lower of two curves, how do we model it? Parallel resistances, mobilities, what is the rule? What is the rule?
Sort of mobility with respect to the field.
No, anything, right?
Hmm.
So you remove the mobility from electric field point of view. Tell me how do I model this? For example, I have one line EC, one line E. I need to get the lower line. How will I get that? Let's say this line is E effective. So what will be E effective? Can I write this? Can I write this? The lowest one will dominate, right?
Oh, yes, sir.
So we have already seen, right? In case of mobility, in case of resistances, you remember, right? In case of mobility, we just had like this.
Yes, sir.
1 by mu equal to 1 by mu 1 plus 1 by mu 2. Let's say this is mu 1, this is mu 2. So the lower one will dominate, right? The same
Hmm.
model we can use here as well. So if I write 1 over E effective is equal to 1 over E plus 1 over EC. So what will be your E effective? 1 over EC. Now take 1 over E common. E by EC, right? Now you need to find out VD effective, that is this line, mu 0 E effective. What will be that? Mu 0 E over 1 plus E by EC. So let's say mu 0 is what? VD max divided by EC times E by 1 plus E by EC. So can I write VD effective is equal to VD max times E by EC divided by 1 plus E by EC. So this is a smooth model or very simple and first order model of velocity saturation. Okay. So we'll see, because I have not derived the current voltage characteristics for your MOSFETs. So I planned it to do it with including velocity saturation. So that I'll do now. It is very simple. Okay. Just you have to follow what I am doing. So your MOSFET model, you know, right? The MOSFET model in linear is mu 0 Cox W by L VGS minus VTH times VDS minus VDS square by 2. This is, you know, right? This is without velocity saturation. Okay. Now, let's say your J drift in your MOSFET will be Q N mu E, right? Or in other case, this E, this part, you can write as VD max times E by EC. So this is E effective. Let's say this is U0. VD max E by EC 1 plus E by EC. Okay. Is it clear?
Yes, sir.
Now your ID will be area. Let's say T inversion times this J drift. That will be W times T inversion times Q N VD max E by EC divided by 1 plus E by EC. So what is this? Basically, if these are your N plus regions, so this is your W. Your currents are flowing in this direction, right? In this direction. So what will be your cross section? The inversion layer thickness
Hmm.
times this W, right?
Yes, sir.
So this is your cross section. So now what is your inversion charge density per unit area? This is Qi per unit area means what? Per unit WL, right? If you are not comfortable with this, let me know at this moment only. So Q times N is volume inversion charge density times this thickness is T inversion, will give you per unit area charge density. So I can write this as to be W times Q inversion times VD max E by EC 1 plus E by EC. Fine.
Yes, sir.
And what is your QI? You remember your QI is a function of, in inversion we are talking about, right? It
Yes,
is
sir.
Cox times VGS minus VTH minus the channel potential, or
Hmm.
let's say VC of X. Channel potential is this VC. So VC of X is equal to VD at drain equal to Vs at source. Fine. So now your ID will be what? This minus sign will be taken care by this. Okay. So ID will be what? If I just simplify it, W times Cox times VGS minus VTH minus VC of X, right? Times VD max times E by EC divided by 1 plus E by EC. Fine. And what is this E? Electric field that we have been talking about. What is this electric field? This is the drain electric field, right?
Yes, sir.
This direction. So it is the electric field of this direction. So that is nothing but minus dVc by dx. So what you can do, you will have id 1 plus e by ec, 1 plus e by ec equal to minus w times cox vgs minus vth minus vcx vd max times e, I am replacing it with minus dvc by dx, right? And divide by ec. This ec I am bringing it to the denominator. Fine. So you can see this is your mu 0, right? From definition. So now your id 1 plus 1 over ec dvc by dx is equal to w cox mu 0 vgs minus vth minus vcx times dvc by dx, right? You can simply multiply everything with dx. So you will have id times dx minus, then you will have id times 1 over ec dvc equal to w cox mu 0 vgs minus vth minus channel voltage times dvc. Now you integrate this from source to drain. For potential, the source side will be Vs, it will be Vd. For distance, so this is for distance, Then this is for source drain. So in this case, it will be Vs Vd. It will be 0 L channel length, right? This is how you get your original equation of that as well, right? So if you simplify and solve it, your ID will be W times by L mu 0 Cox VGS minus VTH minus VDS. This is times VDS minus VDS square by 2. Divide by this entire thing that is due to, this is the VSAT part, right? Velocity saturation part. That will come to the denominator and it will treat it as 1 plus VDS divided by channel length times EC. Okay, this is your total velocity saturated ID lin expression is.
Sir, how did we get that VDS plus L by EC, sir?
Uh, which one?
The
The
denominator.
denominator. Okay.
Hmm.
So here you will get L, right? Here you will get what? Your ID by EC will be, so ID. Okay, just hold on. So here you will get ID times L, right? Here you will
Yes.
get ID by EC times VDS.
Okay. So what
If
is a
you,
minus, right, sir?
huh?
There's a minus sign, right, sir? I mean to say there is a negative sign, right,
Ah,
sir?
okay, okay. Sorry, sorry. Actually, you can consider this as positive because these electric fields are modulus, right?
Okay.
These electric fields are modulus. I think that I have not explicitly mentioned. Okay, these electric fields are modulus, so this will be plus. So let's keep it plus and keep it plus as well. Okay, so keep everything plus because this electric field, what we are talking about is, see, what is your electric field? Electric field is from drain to source, right? But what you are considering your x location to be x equal to 0, x equal to L. So
Hmm.
electric field has a negative sign already. Fine. So just do the mathematics. Okay. The main purpose is when you get the result, how to read those results. So first thing is that first impact of velocity saturation, first impact of velocity saturation, ID lin or linear region ID is lower. Do you agree with me or not?
Yes, sir.
Because this denominator is always greater than 1, right? It is always greater than 1. And this is the part that I would have without velocity saturation, right? So due to velocity saturation, my linear region current drops. That is one observation. Fine. Now, if L is very high, then no impact of velocity saturation. Can you see that? If L is very high, your this term this term is almost zero, then it is going back to the original equation. For long
Yes,
channel
sir.
devices, that is why no velocity saturation. Fine. Next observation. Severely velocity saturated device. That means the second term in the denominator will dominate. So what will be my ideal in now? What will be my ideal in? W by L mu 0 Cox VGS minus VTH times VDS minus VDS square by 2 divided by VDS divided by L times EC, right? L cancelled, VDS cancelled, and this, if I write down, this will become W times Cox times mu 0 EC times VGS minus VTH minus VDS by 2. Okay. So this boils down to W times Cox times VD max times VGS minus VTH minus VDS by 2. So this is your ideal velocity saturated expression. Okay, is that clear?
Yes, sir.
And how will you calculate that? How will you calculate velocity saturated VDS or VDSat? How did you calculate that pinch off saturation point? If you remember, basically, how do you calculate this point? Again, the same trick, right?
Yes, sir.
I will have my DID by dVDS
Hmm.
equal to 0 and then compute my VDSat. Okay, and it will come out to be something like this divided by some factor. Okay, do this derivation. But the important point is, in short channel devices, if this is your velocity saturation and this is your pinch of saturation, right? This pinch of saturation point is VGS minus VTH, right? So now I want to calculate the velocity saturated current. What current, which region I should be looking at? So my point was that this is the region. Let's say I take two regions, okay? So this region, my ID is velocity saturated, right? And this region, what is my ID? This is also my velocity saturated, because the velocity saturation occurred before pinch of saturation, and the velocity saturation limited or saturated the current earlier. So that current level will be determined by the velocity saturation level, which in case without velocity saturation was being determined by my pinch of saturation. That is why we were getting those square law thing, right? What is my pinch of saturated current? ID sat pinch of saturated current is what? Half mu n Cox W by L VGS minus VTH whole square, right? But in case of my velocity saturated current, from this expression, I can see that my velocity saturation will occur much below VGS minus VTH. So ignore the VDS by 2 term. That gives me ID sat velocity saturated current as W times Cox times Vd max times VGS minus VTH. So what is the difference? In velocity saturated drain current, ID is proportional to VGS, linear. Whereas in pinch of saturated current, this was square law, right? So if you see your ID VG, if, wait a minute. So if this gives me square law kind of characteristics, pinch of saturation, velocity saturation gives me something like this. Okay. So as soon as you see your IDVG characteristics to be linear with respect to VGS in strong inversion, you know that your device is velocity saturated. Is that clear?
Yes, sir.
Fine. So after all this, how does the velocity saturated drain current in ID in short channel MOSFET? ID increases linearly with VGS. Okay. Now, next question we will have, when velocity saturation occurs, the MOSFET saturation drain current depends on MOSFET saturation drain current. That means ID sat depends only on VGS. Velocity saturation is severe. Okay. So dependent on VGS and independent of VDS.
Hmm.
Fine.
So what
Of
about channeling information?
See, again, I have told you, right? These all effects consist simultaneously, right?
Okay.
What we are discussing here, that only one component at a time. Now I am not at all bothered about channel length modulation. If you want to see actual ID-VD characteristics, there will be many things. So your actual ID-VD characteristics will be something like this.
Sir, could you
Okay.
repeat again because there was a connection issue in my
Yeah.
side?
So what I am telling you, depending upon bias voltage and multiple situation, your actual ID-VD characteristics will be something like this. ID-VD.
Okay.
Okay. So you can,
Hmm.
because you are learning it for the first time, so you just consider only one part at a time. Each and
Okay.
every effect are occurring simultaneously in the device, and after all they are getting added, right? Just like the leakage currents, they get added to one another, these effects also occur simultaneously.
Yes, sir.
For example, should I show you this now or later? Okay, let me just save it for later. Okay, I will show you one plot with CLM, Debel, VS, something called SCBE. Okay, this is substrate current induced body effect. Okay, I'll show you the asymptotes, and then you will get to understand that in which region what is happening, right? I think this is very premature to show you now. First, let me discuss all the short channel effects. Okay, then we can come to that. Okay, so this velocity saturation, I hope it is clear now. What is velocity saturation? What is pinch off saturation? And in the short channel device with and without consideration of saturation velocity, what will be the transconductance? So ID sat pinch off is what? Half mu n Cox W by L VGS minus VTH whole square. So your GM sat will be mu n Cox W by L VGS minus VTH, right? This is one formula. Another formula for ID sat velocity saturation is mu n is not there. So we will have W. By the way, did you notice one thing? That this ID lin does not depend on L. That means you do not have any more leverage of reducing channel length, right? By reducing channel length, you cannot increase the current if your device is velocity saturated. Is that clear? This is another consequence of the velocity saturation.
Yes, sir.
So this is W times Cox times VD sat times VGS minus VTH. If I am correct, yes. So your GM sat will be W times Cox times VD sat. Okay. Just plug in the values and you will get this to be around 60 microsiemens, and I think this to be around 50 microsiemens. So your W is 10 micrometer, 10 micrometer, Cox is 10 to the power minus 8 farad per centimeter square, VD sat is VSAT, sorry, this is not VD sat, this is VSAT or VD max basically. This is the same thing as VD max. This is your 5 into 10 raised to 6 centimeter per second. So you can multiply and you will see that you will get 50 microsiemens. Fine. So that is all about velocity saturation. Okay. So which of the following statement is true for a MOSFET operating in the ballistic transport regime? What is ballistic transport? Any idea? So, how does electron move from source to drain?
So by undergoing multiple collisions, right, sir?
Multiple collisions, right? So let's
Hmm.
say I give you some energy band diagram like this. Okay, just make it like this, right? Let's say this is your EC. Okay, this is source, this is channel, this is drain. So you know, right? Your electrons are distributed over energy. That means your electrons, if you draw your Fermi-Dirac distribution, it will be like this. And if you draw your density of state, this is your G of E, this is your F of E, and your product of that and area under that will be the number of electrons. So moral of the story is many electrons are above the energy barrier and many are under the energy barrier, right? So some electrons are here, some are here. The population of electrons in this lower energy are more because, of course, for obvious reasons, any particle in this or any object for that matter in this world prefer to be at the lowest state of energy, right? This is how they are distributed over energy. So this axis is electronic energy, right? Now, these electrons, let me draw it in a different color. So these green electrons are at a higher energy than that the violet electrons. So these electrons can go to drain easily, and these violet electrons also, once it is at this place, can go to drain easily. But how does they travel? They travel like this, downhill. So how do you think that downhill transport is happening? I mean to say, let's say this green electron is traveling right in this location. How it comes down to this location and then again start to follow this location. From this energy to this energy, how does it come down? Did you get the question? An electron is traveling at an elevated energy, but after some time it comes down to the EC conduction band and slides along. So let's say, uh, how do I put it? Have you been into water parks?
No,
Let you have not. So how do I give you that analogy? Okay, just I understand in this way. electrons are traveling at a higher energy, but suddenly something is happening so that it is coming down to the lowest possible energy where it can be free, that is the EC, minima of conduction band, and then travels along the conduction band. So what is happening at this location?
Sir, can
There
I leave
is,
now? Because, sir, sorry to interrupt you, but I have to leave now because I have another class at 5 o'clock, sir.
yeah, sure, sure.
Okay.
So the event here, what is happening is the scattering event. Okay. So, or one collision is happening. If it is phonon scattering, it is collision. If it is ionized impurity scattering, it is Rutherford diffraction, right? So, these collisions are what brings those high energy electrons down to the conduction band, and then let them, this electric field from drain to source is letting that electron slide down the conduction band. So that is how that exact the MOSFET transport happens. Okay, that is why we are concerned about mobility, everything. Right? Mobility is directly related to your scattering event. Now assume that your this distance between source to drain, which is called the channel length, is so small that there is no scattering event, no scattering event in the channel. So electron moves like this, right? Random thermal velocity. It will move like, if without any electric field, it will move like that. Any random direction, right? That is called random with a velocity VTH, random thermal velocity. Now, when electric field is applied, how electron moves? Then they will move like this, randomly, but the mean of those random motions are in a path opposite to the electric field. Okay, that is how generally an electron travels in presence of an electric field. Now, the distance and this each corners are one scattering event or one collision. Okay, the mean free path is basically the path between two collision is called one path. And now this you can take the average of all of these scattering events and how much the electron travels without being scattered, and take that average, and that will give you the mean free path of electrons. Let's say if your channel length is less than this mean free path of electrons, that means what? Before getting scattered, let's say electron would scatter like this. Now you are creating your MOSFET so small that your channel length is much shorter than the electron mean free path. What will happen? Electron will go without any scattering, right? It will go like a bullet. That is what is called ballistic transport. Okay. So now what will happen to these green electrons or these high energy electrons? They will not scatter now. They will just pass like this. So whenever if you see the collected electrons in drain will have a very high energy than what you see in conventional. In conventional case, you receive your electrons at this location, right? at these locations in conventional case because your drain EC is this. But in ballistic transport, some of or many of your electrons will come at a very high energy level. Okay, so this is the ballistic transport. Now, what will it depend on? Everything of the current in ballistic transport will depend on the injection velocity at this level. Okay, because always remember that in MOSFETs, the source channel junction is the main bottleneck of transport. So the injection velocity at the source channel junction, once it is injected, then there is that is sure that it will hit the target or reach the drain without any scattering event. So what will it physically depend on? The injection velocity at which it is being thrown, right? So that is what ballistic transport is. So the drain current is limited by the injection velocity at the source. Does not depend on channel length, right? Because electron can travel beyond channel length as well. If there is no drain, electron can travel beyond channel length at the speed of injection velocity, like a bullet. Mobility of the semiconductor limits the carrier velocity. Of course not. What is the mobility concept in this? There is no scattering, right? What concept of mobility is there? Scattering event within the channel strongly influence. Of course, there is no scattering event. That is why it is called ballistic transport, right? So this is what ballistic transport is, and this is how it is being influenced. Okay, I think this is a good time to stop. LDMOS will start tomorrow and other devices. Okay, yeah, tomorrow means next session. Fine. Any question on this?
No, sir.
Okay. Thank you for joining. See you next Saturday.